Hey guys, welcome back. We got day 6, Colligative Properties today. Talk about colligative properties and what they do with solutions. We got to define what they are and some behavior we can predict from them. Alright, so first up, of course, is what is a colligative property? Well, it is a property that depends on the number of particles in solution. So it's the number of particles in solution, not the type of particle. So it doesn't matter what the particles are, we just need to know that how many there are, right? It's just how many particles are, these properties arise. Okay, and they are. What are these properties? It's vapor pressure lowering, it is freezing point depression, it is boiling point elevation, and osmotic pressure. I spelled osmotic wrong. Alright, so let's look at first vapor pressure lowering. So when we talk about vapor pressure, what is it? What is the pressure of whatever liquid we're talking about above the liquid, right? How much of that liquid evaporated, right? And that pressure is how much gas is there, right? So for an ideal solution, right? And of course, an ideal solution is one in which the interaction between the solute and solvent is similar to the solvent or solute interactions. Right, so we're talking about intermolecular forces that are very similar on scale and type. Right? The vapor pressure. So for an ideal solution, the vapor pressure can be calculated using Raoult's law. That's a horrible law there. Law. There we go. So Raoult's law. Alright. Now, what does Raoult's law say? It says the vapor pressure above a solution equals the sum of the partial vapor pressures. So the vapor pressure above a solution equals the sum of the partial vapor pressures of all the components of the solution. components in the solution where the partial vapor pressure of a component depends upon two factors. One, the first factor that this depends on is how much is present. Which we'll have to use the mole fraction. Which of course is Guy. And then two, how volatile it is. Right? That is, right, the vapor pressure of pure A. The vapor pressure of pure A, whatever A is. Right? So volatile, what is volatile? So there's these two terms that were introduced. Volatile and non-volatile. Alright, what's the difference? Volatile is easily vaporized. And non-volatile has no appreciable vapor pressure. Alright. So things that are considered volatile would be like acetone, which is nail polish remover. Non-volatile, one of the things we consider is water. Right? And so if you've dealt with water and nail polish remover, right, acetone dries pretty fast, whereas water, it can be a while, right? And now it just depends on the conditions and where you're at. Okay, obviously if you're in desert type conditions, water evaporates a lot faster than where you're at, like in the southeastern United States, where it's humid. Okay, so let's look at this. So here's a picture of Rayote's law, and Rayote's law from the book. Let's look here. So I'm going to use green. It'll disappear. Alright, so this is the mole fraction of A. So it's a mixture of A and B. So just look at this one right here for now. This is ideal. A and B here. We got A and B. Okay. So the mole fraction of A, that means this is 0A and this is 100% A. Okay, so the red line here that I'm coloring green is the vapor pressure of pure A, and it's going to increase as we have more A. So right there is the vapor pressure of pure A. So whatever A is, if A is, let's say A is water. Okay, A is water, B is ethanol. I don't know what they are. We'll just make three different things. So that's pure water. This is no water. There's none in there. Conversely, if this mole fraction of A is 1, that means the mole fraction of B is 0. So that means here the mole fraction of B is 1. It's all B. And as you can see, that's the vapor pressure of pure B. So any 2 points on the line, like at 0.6 here, right? If we add them up, right? If you add this number and this number up, you should get that number. So the purple line would be addition of the red line and the blue line. So this is the total vapor pressure, which is the red plus the blue vertically, right? So at 0.8, it's here. It's those 2 points added up to make this point right there. Okay? that's how this chart's working. And so ideally, it's just always, no matter what the mixture is, it's going to be whatever A and B's vapor pressure are. You combine them, and there you go. Now, what actually happens? What actually happens is that if we have strong solute-solvent interactions, okay, right? So that means the intermolecular forces are the same. Like you add something that hydrogen bonds or to water, and water likes it a lot. Near dilute, right? Dilute points where I'm almost all A or almost all B, it's close to predicted. But in the middle, it's way off. I mean, that's a huge deviation. And of course, if we do not have strong intermolecular forces, if we don't like each other much, the opposite's true, right? They want to leave each other. It's still close by the end, but they want to leave each other, all right? And so those are deviations from Rayo's law there. Now, so we are going to focus in with the colligative properties and the non-volatile solutes. So colligative properties and the non-volatile solutes. So pretty much what we're going to assume is that if the solute is non-volatile, its vapor pressure is close to zero. All right? So i.e. P of the solute is 0. 0 towards 0, right? So that means the pressure total above the solution is equal to the mole fraction of, now this is very important, it's the mole fraction of solvent, right? Like water or whatever the solvent is, times the pressure, the vapor pressure of pure solvent. Okay, so this is an example like sodium chloride in water, or sugar in water. Sugar doesn't just vaporize, right? It doesn't just, it's not a volatile substance, either is salt. If I put one of those into the solution, all it matters is the mole fraction of water and the vapor pressure of water. So what's going to happen is, if I put salt into water, it evaporates more slowly than if I put just fresh water. Okay? So the addition of a non-volatile solute to a solvent will reduce the mole fraction of solvent and therefore reduce the total vapor pressure. Alright, so when we add a non-volatile solute, it'll reduce the vapor pressure. Okay. Alright, so alright, what does this do? This gives us two formulas with Rayo's law. Alright, so now this formula we just did, this is for one liquid and one vapor pressure. One liquid, that looks like ore. One liquid and one vapor pressure. What if we have two liquids that mix that are considered non-volatile? So more than one liquid. My ends are not looking good there. I'm sorry. One liquid. One liquid. Alright, I have like two liquids. So what happens here? my solution, the vapor pressure of the solution, is equal to the mole fraction times the vapor pressure plus the mole fraction times the vapor pressure. And so I'll use component 1, or A, and component 2, or B. Alright, so it depends on what we have. Okay, totally depends on what you have. If you have 1, you have 2, it doesn't matter. So let's do some examples of these real quick. Alright, we'll do some examples and then we'll go back to what happens with the phase diagram. So this leads us to the day 6, 71. Calculate the vapor pressure of a solution containing 24.5 grams of glycerin and 135 milliliters of water at 30 degrees Celsius. And the vapor pressure of water is 31.8 torr. Assume glycerin is non-volatile. It gives you the density of water. So we have one vapor pressure here for water. Just one. Right? And that's 31.8 torr. That's very important. Okay, so I need the mole fraction. So my pressure of the solution will equal the mole fraction of water, the solvent, times the pressure of pure solvent, H2O, in this case. All right, well, we know what the pressure of H2O is. It's 31.8 torr. That's easy. I need the mole fraction. So water, I have 135 milliliters of water. And we know that 1 milliliter of water is 1 gram. And we further know that 18.02 grams of water is 1 mole. So it turns out that I have 7.49 moles of water. Now glycerin, right, we have 24.5 grams of glycerin and we have C3H8O3. So 24.5 grams of C3H8O3. We know that's 92.11 grams of C3H8O3 is 1 mole, the molar mass. And so that gives us 0.266 of C3H8O3. Alright, so my pressure of my solution will be equal to the mole fraction times 31.8. Right? Because, again, if the mole fraction is 1, the vapor pressure is 31.8. If the mole fraction is less, which it is, it's going to be less than 31.8. So my mole fraction would be 7.49 over 7.49 plus the 0.266. So that means my pressure of my solution of water here would be 30.7. Which makes sense because it's mostly water, right? I mean, 7.5 out of basically 7. Let's call it 8 moles, right? It's mostly water, so that kind of makes a lot of sense. Okay, the next problem is 73 here, and this solution contains 50 grams of heptane and 50 grams of octane. And it gives you pressure at 25 degrees Celsius for heptane and for octane. What's the vapor pressure of each component, and what's the vapor pressure total? Alright, so we need to know the moles of each, right? Because overall, we're going to have pressure of the solution, or total, is equal to the mole fraction of hexane times the pure hexane plus the mole fraction of octane times pure octane, right? That's what we got. And so if I have 50 grams of C7H16, we know 1 mole of C7H16 happens to be 100.23 grams. So that turns out to be 0.499 moles of C7H16. I'm assuming 3 sig figs. There's only one in the problem, so it'd be 0.5, and that's fine if we're going to do 0.5 and one up being 0.4. But right now I'm just going to keep doing 3 sig figs because most of your problems will have 3 sig figs in your textbook. Some will have 2. All right, 50 grams of C8H18. Right, so 1 mole of C8H18 happens to weigh 114.26 grams of C8H18. 0.438 moles of C8H18. Alright, so now if you, again, going back to the sig figs, if you want to use 0.5 and 0.4, that's great. I'm going to use these numbers, and that's fine. Probably going to get the same answer overall anyway. But, so let's do heptane first. We'll do P heptane, right, is equal to the mole fraction of heptane times the total pressure of heptane. So, the pressure of heptane would be equal to the mole fraction, which is 0.499. Now, these moles here, what's the total moles? Right? The total moles would be 0.499 plus 0.438. And so that would be 0.937. Okay, 0.937 times, now heptane was 45.8. So notice that heptane has a higher vapor pressure than octane, right? Because octane has more intermolecular forces than heptane because it's bigger. Kind of fun. And so this turns out to be the pressure of heptane, 24.4 torr. Fun stuff. Let's do octane now. Pressure of octane is equal to the mole fraction of octane times the pressure of octane. So that would be 0.438 over the 0.937 moles times 10.9 torr, and that would be what, 5.1010. Oh, it didn't change back to orange. I apologize for that. Let's change it back to orange. 10.9 torr, and that equals 5.10 torr. Okay, so my total pressure would be equal to the pressure of heptane, which is 24.4 torr, added to pressure of octane, 5.10 torr. So that total pressure will then be, looks like 29.5 torr, 30 torr if you want to use 1 sig fig. Alright, so there's 2 vapor pressures. So we just did with 73, 2 vapor pressures, 2, alright, and 71 was 1 vapor pressure. So hopefully that makes sense.